Having talked about partial pressures and the relationship between the ideal gas law and a gas's density and the molar mass of a gas, we're now ready to talk about making predictions about gas phase chemical reactions. And it's very important to have a skill set to talk about and make quantitative predictions about what happens in gas phase chemical reactions, because many of the most important industrially relevant and environmentally relevant chemical reactions that you might be interested in occur in the gas phase. And the tricky thing about gas phase chemical reactions is that everything you learned about balanced chemical reactions applies to gas phase chemical reactions. How to predict a theoretical yield, how to identify a limiting reactant, all these things still apply to gas phase chemical reactions. The challenging thing is that unlike chemical reactions that you talked about with solids or liquids, where you use the mass of the reactant and the molar mass to figure out how many moles of the reactant you have, or aqueous in water chemical reactions where you use the concentration of the reactant and the volume that you use to figure out how many moles you have, gas phase reactions have a different handle for figuring out how many moles of the chemical are about to participate in the chemical reaction. And the ideal gas law is how you relate fundamentally the pressure or a volume of a gas sample to the number of moles of the gas that are in that sample. And so between the ideal gas law and Dalton's law, we have a robust tool set that will allow us to calculate how many moles of a gas phase reactant or product we have in a gas sample that consists of a single gas, or even in a gas sample that is a mixture of gases. So we can now apply what we already know about reaction stoichiometry to gas phase chemical reactions. And the missing piece of that was knowing how to use the ideal gas law to link pressure or volume of a gas to number of moles. The idea being everything we know about gas phase, chemical reactions in general, still applies to gas phase chemical reactions. So for instance, if we're interested in a reaction like the Haber-Bosch process, where nitrogen, N2, reacts with 3 moles of dihydrogen, H2, to make 2 moles of ammonia, we know how to read a balanced chemical equation like this to say that if I have 1 mole of dinitrogen, I'm going to need 3 moles of dihydrogen if I want to make 2 moles of ammonia with no nitrogen or hydrogen left over. If I have 1 mole of ammonia and 3 moles of dihydrogen, I have stoichiometric amounts, and I would expect to make exactly 2 moles of ammonia using this chemical reaction. Everything we know about balanced chemical equations, identification of limiting reactant, calculation of theoretical yield, still applies to gas phase reaction. The hard part about gas phase reactions is instead of being given an amount, like a mass, here's 180 grams of nitrogen, here's 120 grams of hydrogen. For most gas phase reactions in the real world, you're going to have a pressure or volume measurement to describe the amount of a gas. And so what the ideal gas law allows you to do is say, if I have a pressure of 1.5 atmospheres of nitrogen under these volume and temperature conditions, how many moles of nitrogen do I have? Or if I have 60 liters of hydrogen at 1 atmosphere of pressure and 25 degrees Celsius, according to the ideal gas law, how many moles of hydrogen do I have? So the only thing that's going to be different about describing the chemistry of gas phase reactions is that the ideal gas law is now your way in and out when you're talking to the balanced chemical equation. You use the ideal gas law to figure out how many moles of a gas you must have if you have 1 atmosphere of pressure of that gas under these conditions, or 30 liters of the gas under those conditions. And so what the ideal gas law does is allow us to link things that we can measure about a gas to the number of moles of the gas that must be there. And so we're going to change our thinking a little bit, where now when we think about gas phase reactions, instead of thinking about kind of individual molecules as our picture or our diagram in cartoon form, we're going to think about, I have this volume of nitrogen, I have this volume of hydrogen. if I have those volumes of my reactants, do I have stoichiometric amounts to make exactly this much volume of ammonia? And the ideal gas law is going to be that piece that allows us to link a volume of a gas to the number of moles of a gas. And once we know the number of moles, we can make predictions about gas phase chemical reactions in the usual way. But you have to be able to use that complete toolkit. You have to be fluent in the ideal gas law, and you have to be fluent in the fundamentals of reaction stoichiometry. So before you go back and check out the examples that are coming up, if it's been a little while since you've looked at identifying limiting reactants, used balanced chemical equations to make a prediction about the yield of chemical reaction, go back to the earlier chapters in your textbook and brush up on some of that terminology and how that thinking works. If you still can't quite remember how to identify limiting reactants, what it means to have stoichiometric amounts of reactants, etc., that's a great thing to bring to office hours or to bring to our Zoom-based recitation sessions and ask some questions about those fundamentals, because those concepts are never going away while you're studying chemistry or while you're working in a field that's related to chemistry, and you want to be rock solid on those. Otherwise, solving these problems is going to be a lot harder than it has to be. So come back in a few minutes. We're going to look at a number of examples where we combine what we already know about making predictions about chemical reactions with what we've learned about Dalton's law and the ideal gas law.